To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. So I am going to continue with the lesson electronics. In the previous chapter, we discussed about conductors, insulators and semiconductors. So as we already discussed, you all know the group 4 elements like silicon, germanium, they have 4 electrons in their valence shell. And normally, they exist as crystalline lattices. Why? In order to obtain the electronic configuration with 8 electrons, that is a stable electronic configuration. So we understood that one silicon atom bonds covalently with another 4 silicon atoms in a crystalline lattice structure. So there, when the temperature is about 0 Kelvin, that is a low temperature, all the bonds are complete. And there are no free electrons, no charges. So therefore, the crystalline lattice does not conduct electricity. But when it comes to a higher temperature, for example, room temperature, you all know it's about 300 or over 300 Kelvin. Then, of course, that thermal energy that is available in the environment is enough to break some of the bonds. So, some electrons from the bonds come out of the bond. And therefore, there is a hole generated and that acts as a positive charge carrier and the free electron is a negative charge carrier. And in a crystalline lattice, there will be equal number of positive charge carriers holes and negative charge carriers electrons. So therefore, the lattice is electrically neutral. But both the electrons and holes, they can move. Therefore, both of them contribute to conducting electricity. And also we discussed that the electrons flow from negative to positive terminal when a potential difference is applied across a semiconductor material. At the same time, holes move from positive to negative as well as the conventional current flows from positive to negative. So that is how the semiconductor works. Then I told you all, based on how these semiconductors conduct electricity, we'll be looking at them as intrinsic semiconductors and extrinsic semiconductors. So now in this chapter, I will first discuss intrinsic semiconductors. So this is same as what we discussed before. Now here you can see pure semiconductor materials such as silicon and germanium that exist in crystalline form as mentioned above are known as intrinsic semiconductors. So what we already discussed. So here it is both silicon and germanium that exist in crystalline form as mentioned above are known as intrinsic semiconductors. So this is when the semiconductors conduct a small amount of electricity at room temperature or higher temperatures greater than 0 Kelvin. So that is an intrinsic semiconductor. Then we will look at the effect of temperature on the conduction of electricity. Now to understand that, if you take a conductor, now if we have a normal conductor here, if it is a conductor, there are free electrons. Now I will use blue color dots to denote the free electrons. Now when temperature increases, what will happen to the thermal energy of these electrons? You all know the thermal energy increases. Usually when the thermal energy or heat energy increases, that can increase the kinetic energy of particles. So because of that, the electrons also get more kinetic energy and therefore they start moving randomly, not in an orderly manner. Instead, they start moving in all different directions. Random movement. So, because of this random movement increases, the resistance of the conductor increases. So, because of that, now here you can see a conductor, when temperature increases, random movement of electrons, that also increases. Because of that, the resistivity increases. If the resistivity increases, what will happen to the conductivity or the conducting ability of the conductor? That will decrease. So here, conductivity or conductance will decrease. So that is what happens in a normal conductor. In a conductor, when the temperature increases, the free electrons start moving more randomly. Because of that, the resistance increases and the conductivity decreases. But if you look at a semiconductor, now in a semiconductor, if we have a semiconductor, there, what will happen is the number of electrons and the number of holes. I'm just writing it together so that you know they are equal in number. These will increase when we increase the temperature. So here in semiconductors, when temperature increases, number of charge carriers. Here there are two. One is holes and electrons. They increase. And because of that, resistivity or resistivity decreases and electrical conductivity increases. So, can you all understand how a conductor and a semiconductor works? Now, both the resistance depends on temperature. For a conductor, when you increase the temperature, because of the increased random movement of electrons, the resistance or resistivity increases. Therefore, the ability to conduct electricity decreases. But in a semiconductor, as the temperature increases, the number of bonds that are broken increases. Therefore, the number of charge carriers, that is holes and electrons, they increase, reducing the resistivity of the semiconductor. And because of that, the electrical conductivity of semiconductors increases with increase in temperature. So that is how temperature affects the conductivity of materials. So if I go back, here we can see effect of temperature on the conduction of electricity. So there you can see, since the random motion of free electrons increases as the temperature is increased, a rise in the temperature inhibits the current flow. Therefore, a temperature rise in conductors causes a decrease in the conductivity. That is, increase in the resistivity. So that is what you need to remember. A temperature rise in conductors causes a decrease in conductivity and increase in the resistivity. That is for conductors. But However, in semiconductors, a rise in temperature breaks bonds, generating more holes and free electrons, causing an increase in the conductivity, that is, decrease in the resistivity. However, in semiconductors, a rise in temperature breaks bonds, generating more holes and free electrons, causing an increase in the conductivity, decrease in the resistivity. That is what I explained to you all here. So, I am sure you can understand that clearly. Is that okay, student? So, then I'll move on to the next slide. Here we discuss extrinsic semiconductors. Now, as we discussed so far, students, if you take a semiconductor, as the temperature increases, the conductivity or the conductance of the semiconductor increases. But just because we want the conductivity to increase, we can't keep on increasing the temperature, because you need to have electronic devices working at room temperature, or when the temperature is less than room temperature sometimes. Now, there are places where the temperature of the environment drops. So, then also the particular device should work. Sometimes inside an air-conditioned room where the temperature is less, then also the device should work. So, you can't only depend on the environment temperature or the thermal energy available from the environment for a semiconductor to conduct electricity. So, because of that, they have found another way to make the semiconductors to conduct electricity well. That is why we have the extrinsic semiconductors. Now, we will see what will happen to an extrinsic semiconductor. Now, here we have the silicon lattice. No? Now, silicon lattice. Now, you saw in the silicon lattice, there are 4 silicon atoms bonded to one silicon atom. So, here all the bonds are there. Now, to this silicon lattice, what we do is we mix another material. We mix another material. Mixing group 5 element. Group 5 element. For example, we will take phosphorus. Now, phosphorus, if you can remember how many valence electrons, it belongs to group 5. So, there are 5 valence electrons. Now, when this phosphorus, a small amount of phosphorus is mixed with the silicon lattice, then what will happen is some of these silicon atoms will be replaced by the phosphorus atom. So, if we look at that situation, we will have a phosphorus in the middle instead of this silicon phosphorus. Around that, we will have all the other silicon atoms. Now, here the silicon atom has 4 electrons. Because of that, it can form 4 bonds with phosphorus. But now phosphorus belongs to group 5. So, there should be 5 valence electrons. Only 4 of those electrons involved in forming bonds. There will be an additional electron. Now, there is going to be an additional free electron. Now, this is a free electron. Now, this free electron is there in the lattice structure, and that is negatively charged. Now, if you look at the total number of electrons and the positively charged holes, you will see there are additional free electrons or additional negative charge carriers. Because of that, this particular semiconductor is called the negative type semiconductor. because there are more negative charges than the positive charges. The normal way the holes and electrons are also going to be there. They are in equal number, but there are additional free electrons coming from phosphorus. So because of that, this is a negative type semiconductor, or what we call as N-type semiconductor. N-type semiconductor. Is that clear, students? So we had the normal silicon lattice like earlier, but you mix it with another element from group 5. As an example, I took phosphorus. There are 5 valence electrons and some of the silicon atoms are replaced by the phosphorus atoms because the phosphorus atom occupies the position of a silicon atom. Then what happens is only 4 bonds can be formed because earlier there was a silicon, now there is a phosphorus, but it can combine with 4 silicon atoms. So because of that, there is a free electron from phosphorus. So there are additional negative charges or additional free electrons. Because of that, this type of semiconductor is known as a negative type semiconductor or N-type semiconductor. And the mixing of this particular element, that process is known as doping. This process is called doping. So doping a semiconductor with a group 5 element gives rise to N-type semiconductors. And in an N-type semiconductor, you have to remember, students, these are all new terms that you need to remember. In an N-type semiconductor, now there are more electrons. That is why they are negative type semiconductors. More electrons and less holes. Because of that, in an N-type semiconductor, electrons are known as the majority charge carriers. And the holes are known as minority charge carriers. So here also we have both electrons and holes. Electrons are more in number, so they are known as majority charge carriers, and holes are minority charge carriers. And these electrons are donated by the group 5 atom. Because of that, the group 5 atoms are known as donor atoms. So here, the group 5 element or the atoms are known as donor atoms because they donate electrons, additional electrons to the semiconductor. So these are all different points that you need to remember, students. In an N-type semiconductor, there are more electrons. Because of that, we call them the majority charge carriers. Holes are the minority charge carriers because they are less in number compared to electrons. And group 5 element, that atoms that are known as donor atoms, donate the electrons. And also related to this, you have to remember number of electrons is more than number of holes. That is why we call the electrons as majority charge carriers and the number of holes as the minority charge carriers. Is that clear, student? So I'll go back to the explanation. So now, here if you look at semiconductors, let us consider what happens when a minute amount, now this is important, minute amount of the element phosphorus is mixed or doped into an intrinsic semiconductor such as silicon. So earlier we said intrinsic semiconductor. Why? It is the pure semiconductor. So to a pure semiconductor we mix phosphorus. Here you can see the word doped. I mentioned the term doping. The process of doping gives rise to this mixing of element. So that is doped to an intrinsic semiconductor such as silicon. Now phosphorus is an element in group 5 of the periodic table and has 5 electrons in the outermost shell. So you need to understand that. A phosphorus atom makes the number of electrons in outermost shell 8 by acquiring 4 electrons from 4 nearby silicon atoms around it. So what we discussed. A phosphorus makes the number of electrons by bonding with another 4 silicon atoms. In the process, one of the 5 electrons is left behind without taking part in forming a bond. This electron can move about freely in the lattice. So in the process, one of the 5 electrons is left behind without taking part in forming a bond. And this electron can move about freely in the lattice. So that is what we discussed so far. So I showed you all the diagrams. I'm sure you can understand that. We have the normal lattice. When doping happens, we mix group 5 element, that is phosphorus. So here you can see the phosphorus atom occupies the place of a silicon atom. And to get 8 electrons, it bonds with another 4 silicon atoms. So therefore, there is a free electron. So because there are more free electrons, we call it the negative type semiconductor or the N-type semiconductor. So here in an N-type semiconductor, I told you all, electrons are the majority charge carriers, holes are the minority charge carriers. Why? Because number of electrons is more than the number of holes here. And also the group 5 element, they are known as donor atoms. So the same discussion I will continue in the next slide as well. So here, this is again what I explained to you all. You can see here, students, when there is a phosphorus atom. Now it forms bonds with 1, 2, 3, 4 silicon atoms. So 2, 4, 6, 8, there are 8 electrons and there is a free electron. Free electron. So a silicon lattice doped by phosphorus. So like this, there will be many free electrons. So that is how the doping occurs. Then, figure shows how a phosphorus atom forms bonds with silicon atoms. The electron left behind increases the conductivity of the lattice. So that is important. The electron left behind increases the conductivity of the lattice. Since negatively charged electrons are introduced to the lattice as charge carriers, the semiconductor is known as negative type or N-type semiconductor. Semiconductors whose carriers have been increased by doping it with another element are known as extrinsic semiconductors. So this is also important, student. So when we say extrinsic semiconductors, this part is important. Now, semiconductors whose carriers have been increased by doping it with another element. are known as extrinsic semiconductors. So I told you all there are two types. Now here you can see this. Yes. So we looked at the semiconductor, pure semiconductor at a higher temperature than 0 Kelvin, that is, let's say, room temperature. Because of the thermal energy, there are free electrons and holes, but still the lattice is electrically neutral. Then they conduct a small amount of electricity. We call it as intrinsic semiconductors. But when you dope them, when you dope the semiconductor by a material, and because of that, the carriers have been increased, then we call it an extrinsic semiconductor. So I told you all about two types. The pure semiconductors, which conduct a small amount of electricity, are the intrinsic semiconductors. The pure semiconductor after doping with another element. Now we discuss the group 5 element. We will be discussing group 3 elements also, doping with group 3 elements. Then when they are doped with another element, they are known as extrinsic semiconductors. Is that clear, students? So then I will move on to the next slide. So here you can see, by doping an intrinsic semiconductor with other elements in group 5 such as arsenic and antimony, also N-type extrinsic semiconductors can be formed. So here you have to remember, by doping a semiconductor with other elements in group 5 such as arsenic, antimony, also N-type extrinsic semiconductors can be formed. And also, since electrons are donated to the lattice by group 5 elements, they are known as donor atoms. So what I explained to you all before. So if you all look at this periodic table, again I put it so that to recall what we have learned before. Here you can see, students, if you look at the group 5 element, can you see the group 5 elements? Now we looked at phosphorus, then we looked, I said here it says arsenic, antimony. They all belong to group 5. So silicon, germanium, those are the group 4 elements. You dope them with group 5 elements to get the N-type semiconductor. So one of these can be used to get the N-type semiconductor. Is that clear? N-type semiconductor. So doping is the mixing of another element. It can be either from group 5 or group 4. So after doping, if you get the semiconductor, that is known as the extrinsic semiconductor. So now in the next slide, we will see how we can dope the group 4 silicon or germanium with a group 3 element like boron. That is what I will discuss after this. Here you can see, if silicon, which is an intrinsic semiconductor, is doped with an element in group 3 such as boron, the boron atom forms bonds with nearby silicon atoms. So there you can see, if silicon, which is an intrinsic semiconductor, is doped with an element in group 3 such as boron, the boron atom forms bonds with nearby silicon atoms. However, since there are only 3 electrons in the outermost shell of the boron atom, there is deficiency of 1 electron in order to form 4 bonds. So if we look at the figure now. So here silicon again is the silicon lattice doped by boron. So what happens? Again, a boron replaces one of the silicon atoms. Now there are 4 silicon atoms surrounding it, 1, 2, 3, 4. So here you can see this boron is bonded with the silicon, both electrons are there. Here also the silicon is bonded, here also silicon is bonded. But if you look at these two, the boron and silicon, silicon gives an electron, but the boron only has 3 electrons, which have already been used up. 1, 2, 3 electrons of boron have been used up. So, because of that, there is an empty space there, absence of electron. So, already you all know if it is an absence of electrons, it is a hole. So, here there is a hole. So, when you dope silicon or germanium with a group 3 element, the valence electrons are 3. Because of that, more holes are present. More holes than electrons. So here you can see, earlier if it had been silicon, all the electrons would have been there. But now because it is boron, there is 1 electron missing and we have a hole there. So there are more holes than electrons. So then what do we call this? There are more positive charges than negative charges. Because of that, this is known as the positive type or p-type semiconductor. P-type semiconductor. So this is a p-type semiconductor. When you dope a silicon lattice with group 3 elements, because the group 3 element has only 3 valence electrons, there will be deficiency of electrons. So therefore, there will be more holes than electrons. And then we call the semiconductor as a positive type or p-type semiconductor. This is also an extrinsic semiconductor. Now in this one, in a p-type semiconductor, more holes than electrons. So what will be the majority charge carrier? Holes will be the majority charge carrier, and electrons are the minority charge carrier. And what do we call the group 3 atom? Those are called the acceptor atoms. Here they don't donate electrons. Instead, they take up electrons from the lattice. But here there is a hole that can accept electrons. So because of that, the boron is known as the acceptor atom. Boron, that is group 3 atom is known as the acceptor atom. Is that clear, student? So this is the second type of extrinsic semiconductor. When you dope the semiconductor, that is group 4, silicon or germanium, with group 5, we get the N-type semiconductor. When you dope them with group 3, you get the P-type semiconductor. So if I go back to the slide, you can see here, if silicon, which is an intrinsic semiconductor, is doped with an element in group 3, such as boron, the boron atom forms bonds with nearby silicon atoms. However, since there are only 3 electrons in the outermost shell of the boron atom, there is a deficiency of 1 electron in order to form 4 bonds. The figure shows how the atoms and bonds are configured in this case. So here I explain to you all, since group 3 has 3 valence electrons, there are more holes because there is not enough electron in boron to form a bond. So because of that, there are more positive charges than negative charges. Therefore, this semiconductor is known as a positive type or P-type semiconductor. And in this P-type semiconductor, there are more holes than electrons. Holes are known as the majority charge carriers. Electrons are known as the minority charge carriers. And boron, that is the group 3 atom, is known as the acceptor atom. I'm sure you all can understand that. So with this, students, I'll move on to the next slide where we continue with the discussion. So here we can see a hole exists at the point where the electron is deficient in the boron atom to form a bond. So that is what we saw in the previous diagram. So a hole exists at a point where the electron is deficient in the boron atom to form a bond. Since holes can conduct electricity as positive charges, the conductivity of silicon increases. So that is also something you know. A hole is equivalent to a positive charge. A hole is equivalent to a positive charge. And such extrinsic semiconductors are known as positive or P-type semiconductors. A positive or P-type semiconductors. Then, so because the hole concentration in P-type semiconductors is much greater than the electron concentration, holes are called majority carriers and electrons are called minority carriers. Now here, students, there is a printing mistake in the book. This should be carriers. C-A-R-R-I-E-R-S, carriers, not C-U. It should be C-A-R-R-I-E-R-S, carriers. So the hole concentration is more. Because of that, holes are called the majority carriers and electrons are called minority carriers. So then, by doping an intrinsic semiconductor with other elements in group 3. So here we can do that with other elements also. So other elements in group 3 such as aluminium, gallium and indium. Instead of boron, also P-type extrinsic semiconductors can be formed. Since holes that can receive electrons are produced by group 3 elements, they are known as acceptor atoms. So group 3 elements are known as acceptor atoms. All what I discussed with you all before. So I'm sure you can understand that clearly, students. So with that, I will move on to the next slide. Here again, I have put the periodic table. So like we discussed before, here you can see this is the part where we are concentrating on. Now we have the 2 semiconductors, silicon and germanium. To that, what did we do? We doped phosphorus, arsenic, antimony, group 5 elements. You get the N-type semiconductor. N-type semiconductor. But if you dope it with group 3 elements such as boron, aluminium, gallium or indium, then of course you will get P-type semiconductors. Is that clear? So you have the semiconductor, silicon and germanium. That is normally the intrinsic semiconductor. But when you dope them, we call it the extrinsic semiconductor. And when doping is done with group 5, N-type semiconductor is obtained. When doping is done with group 3, we get a P-type semiconductor. Is that clear, students? So you should be able to compare the two, the P-type and N-type semiconductors. Is that clear? So if we do that here, here you have the intrinsic semiconductor, then we have the extrinsic semiconductor, under that we have the N-type and we have the P-type. So in this, here we have, if you put it like that. Now, intrinsic semiconductor, pure semiconductor. So it can be silicon or germanium. Now, extrinsic semiconductor, what do we do? Doped with group 5. Example, silicon with phosphorus. Or you can use arsenic, antimony also. Those are the group 5 elements. Here P-type doped with group 3. Example, silicon with boron, aluminium, gallium or indium. Then now if you consider the number of electrons and holes here. Here number of electrons equals number of holes. Here in N-type, more electrons than holes. So here more holes than electrons. So if we continue with the table, so there because of this we call majority electron carriers. Carriers are electrons. Here they are holes. And minority carriers are holes Here they are electrons. But here, because the number of electrons are equal to number of holes, these are electrically neutral. Neutral. Is that clear? Then the last point. Here, the group 5 element, group 5 atom is the donor atom. Donor atom. And here, group 3 atom is the acceptor atom. So those are all what we discussed so far. Intrinsic, extrinsic semiconductors. Is that okay, students? So all what we discussed, I have summarized here. If it is the pure semiconductor, silicon or germanium, we call it the intrinsic semiconductor. They conduct a small amount of electricity at a higher temperature. Due to the thermal energy, some of the bonds are broken and the electrons come out as free electrons, and because of that they conduct electricity. But in an extrinsic semiconductor, we have to dope it with another element. So if it is N-type, we dope it with group 5. That is example, silicon with either phosphorus, arsenic or antimony. But if it is a P-type semiconductor, we dope with group 3. That is example, silicon with boron, aluminium, gallium or indium, any of the group 3 elements. Then, if you look at the number of electrons and holes, in an intrinsic semiconductor, number of electrons equals number of holes. But in N-type semiconductors, that is extrinsic semiconductor, there are more electrons than holes, whereas in P-type, there are more holes than electrons. And if you look at the intrinsic semiconductor, they are electrically neutral. Why? Number of electrons are equal to number of holes. But here, in an N-type, majority carriers are electrons, minority carriers are holes. But in a P-type, majority carriers are holes and minority carriers are electrons. And finally, we saw that the group 5 atom is called the donor atom because it donates an electron. Whereas the group 3 atom that generates the hole is known as an acceptor atom. Is that clear, students? So we discussed all these so far. And with that, I am going to end this chapter, and in the next chapter, we will try to understand what will happen if we combine the N-type semiconductor with a P-type semiconductor, or if we have a semiconductor material that can be doped with two different elements. For example, now here, if you have a semiconductor like that, then what we do is, this side we dope with group 3. Let's say boron. Then what will happen? Part of this will become a P-type semiconductor. At the same time, on this side, we dope with group 5. For example, phosphorus. Then it will become N-type. So here on this side, it will become N-type. And in between, there will be a region. But here you have P and N. They will both meet together. And that is known as a PN junction. So here we will have a PN junction. PN junction. So like I said, in the next chapter, I will explain how this PN junction will function. And also how we can use that to make electronic devices. Is that clear, students? So with that, I am going to end this chapter, and as we start the next chapter, we will discuss what PN junctions are.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.